section we're going to talk about are solids, and I essentially just want to go through our different types of solids. For each type, we're going to talk about what types of particles they're composed of, what kind of connections are holding them together, and then an example. So types of solids. And we actually do have two fundamental types, two basic types. One's going to have subtypes, the other, no, it's not. So two basic types. And I'm going to do the one that doesn't have subtypes first, and that's an amorphous solid. And I'm going to leave a little space and then put the second one. Sometimes it's easier to describe them if you can compare and contrast. So our second one are crystalline solids. So our big difference between the two is that crystalline solids have an order to them. So the particles have a particular arrangement, and that arrangement stays over a long range, right? It has a repeating pattern. Amorphous solids, I don't have that repeating pattern. There's no real order to how the particles are put together. So crystalline solids, the atoms, molecules, ions, whatever it happens to be that's making it up, have a long range order. So there's some sort of pattern, and then that pattern just repeats itself. So if I had a particle here, one in the middle, and then these were connected with intermolecular forces or whatever the connections happen to be. So let's say that was my pattern, then that pattern just repeats. So we could go off to the side, we have one in the middle. I'm not very good at drawing, but it just has a repeating pattern, right? That one in the middle. And that pattern just keeps going and going. I could draw another one down below, but it just keeps the same pattern over and over again. Because of that, they tend to have sharp corners, they have flat edges, they're pretty well defined. You can actually see the pattern over a long range. If you think like a crystal, if you just think like the rock crystal, they have sharp edges, a piece of rock salt also. So sharp edges, flat surfaces, you can actually see it, like I said, over a long range. Amorphous solids, these don't have a repeating pattern. So no long range order to its constituent particles, right? The particles that make it up. An example of an amorphous solid, sometimes it's easier if I just give you an example, rubber, right? You don't think of rubber as having sharp edges or flat sides, it's just kind of a blob, it doesn't have a pattern. Where these guys, sharp edges, flat surfaces, etc. So amorphous versus crystalline. Most solids are crystalline solids, and a few examples for us, or a few different types, so subtypes. So under crystalline, our first one is going to be an ionic solid. And a lot of these are actually just as they sound. An ionic solid is composed of ions. Remember I said I wanted us to know what it's composed of. It's held together with ionic bonds, so that's how they're connected, and then any ionic compound, sodium chloride would be an example. So an ionic solid, the constituent particles are ions. Remember, ions are charged atoms held together with ionic bonds. Remember, ionic bonds are oppositely charged atoms being attracted to each other, right? There's a transfer of electrons. One's losing them, becoming positively charged, another gains them, becomes negatively charged, and then those oppositely charged ions are attracted to each other. An example, sodium chloride, any ionic compound that you want to use. If we were to draw one out, I could have sodium, and I'm just kind of making up the pattern. It probably has a distinct pattern. I just am not looking for that level of detail. But each sodium, let's actually draw a couple, is surrounded by and bonded to many chlorine. And then each chlorine is surrounded by and bonded to many sodium. So these guys all have opposite charges, so they're all attracted to each other. Right? We could go back to a chlorine here. We could have a sodium over here. And those guys are attracted to each other. I got lazy on you, didn't switch colors, but all of those dotted lines that I'm drawing are ionic bonds. So each of the ion is surrounded by ionic bonds. So ionic solid made up of ions held together with ionic bonds. An example would be an ionic compound. Our second one are molecular solids. And I bet you'll never guess what their constituent particles are. Yeah, you got it. They're made up of molecules, right? Ionic solids are made up of ions. Molecular solids are made up of molecules. So the constituent particles are molecules. And these are held together with intermolecular forces. We can subdivide them if we wanted into polar molecular solids and non-polar molecular solids. The polar ones obviously would be polar molecules that make them up. So they'd be held together with London dispersion forces, dipole-dipole forces, and possibly hydrogen bonds. Our non-polar molecular solids obviously would have non-polar molecules that comprise them, and they would be held together only with London dispersion forces. Any sort of molecule, we could use water as an example, that would be a polar molecular solid. We could do dry ice, CO2 solid. It's non-polar. If you draw it out, it's linear. So my bond dipoles actually cancel each other out, and it's a non-polar molecule. So that would be a non-polar molecular solid. We could do sucrose, table sugar. Any sort of molecule would be held together in its solid form with intermolecular forces, also in its liquid form. I'm going to use water. I just want to compare and contrast to our ionic solid. So when I draw water, what I'm doing is I'm drawing my covalent molecule. So that bond between oxygen and hydrogen is a covalent bond. And then I would draw my neighboring molecule. And then when I draw my connections between them, right, when I draw that dotted line, that's my intermolecular force. I could draw another water in here if I wanted. And then that's another intermolecular force. So for water, we could keep going, but my dotted lines are different than my solid lines, right? Within a unit, within this guy, right, I have covalent bonds, and then between molecules, I have intermolecular forces. If I go back and look at this one, they're all the same. Every single one of these connections, though I used two different colors, that was because I was lazy and didn't switch. Every single one of those connections is the same. So it's not like I have a unit that then has a different connection to another unit. I just have ions that are connected. Every single one of those bonds is the same. Here, the part that I've highlighted in yellow is different than what I didn't highlight, right? I have covalent bonds that are held together with intermolecular forces. My ionic solid is just ionic bonds. My third type are covalent network solids. Sometimes the word network isn't included, so if you just hear covalent solid, it's the same thing. So again, the word network doesn't have to be there, covalent solid. And these are actually just really like one big molecule. So it's atoms or small molecules that are attached to each other with covalent bonds. So atoms, generally non-metal, so non-metallic atoms, or small molecules. And they're connected with covalent bonds. And an example for us, a diamond. Graphite, we can do graphite also. I don't know if that's how you spell graphite, sorry guys. Quartz is an example. I'm gonna draw, I guess a diamond. So it's just a whole bunch of carbons that are attached to each other. And these guys actually form hexagons. Oop, missed a carbon. And then that pattern just kind of repeats itself again. So if we want to compare and contrast again, all of these connections, use my highlighter again here, all of these connections are the same. It's kind of similar to our ionic solid, where I don't have a connection between a unit and then those units are connected to each other, like I have with my molecular solid, right? I have water as a unit, water is another unit, and then a different connection between them. This, all of those connections that I just highlighted are the same. It's all covalent bonds. Just like my ionic solid, all of those connections are the same. They're all ionic bonds. So kind of similar to my ionic solid, it just happens to be only non-metal atoms. They're not ions, they're not charged. And then they're connected with covalent bonds. Remember, in covalent bonds, we're actually sharing electrons, right? We're overlapping orbitals. So it tends to be really strong. If you think a diamond or quartz, those are very strong things. So a covalent network solid. And then my third one, or my fourth one, I guess, D. These are metallic solids. It's made up of metal atoms. And then it's held together with metallic bonds. When we talked about types of chemical connections earlier in the semester, which honestly seems like a lifetime ago, right? We had three types: ionic, covalent, and then metallic. And we said metallic was between a metal atom and another metal atom, and the electrons were shared. They're actually delocalized, and we weren't going to go into a lot more detail. I'm still not going to. Just know that metallic solids are made up of metal atoms, and they're held together with metal bonds. We could do any sort of example, right? If I had a gold bar, if I had a piece of aluminum, any sort of just metal. It could be an alloy too, so something like brass, which is a combination of different types of metals, would also be a metallic solid. From a property standpoint, I don't know that we talked about this when we talked about the difference between metals and non-metals, but things that are metallic tend to have, they're good conductors of heat and electricity. They tend to be malleable, so you can like bend them and shape them into different forms, that sort of thing. So all of the metallic properties that metallic, it's very redundant, metallic elements have, the solid also has. So again, be able to explain the difference between them, know what the particles are that make them up, know how they're held together, and then give me an example. I think they're pretty straightforward because it's really in the name. An ionic solid is made up of ions held together with ionic bonds, an example of an ionic compound. Molecular solids, they're made up of molecules, they're held together with intermolecular forces, and then anything that's a molecule you could give me an example of. Covalent network solids, These guys are my non-metal atoms. They're connected with covalent bonds. And remember we had said when we were talking about types of chemical bonds that covalent bonds are typically between a non-metal and a non-metal. And then my metallic, made up of metal atoms held together with metallic bonds. So the next section is on phase changes, which I'm going to do really fast. You guys have talked about phase changes in previous chemistry classes. So this is like what happens when we go from a solid to a liquid, what's the name, that sort of thing. So phase changes, changes in state, however you want to say it. Changes. So there are types of physical changes. Remember, physical changes are changes where we don't change the chemical identity of it. So going from water to water. Remember, it doesn't have to be a phase change. Phase changes or changes in state are not my definition of a physical change. They're only types of physical changes. Right? If I was to take a piece of paper and rip it into tiny pieces, it didn't change state, but it is a physical change. It was cellulose before, it's still cellulose. It was solid before, it's still solid, but now it's ripped up into tiny pieces. So that's still a physical change. So not all physical changes are changes in state, but changes in state are an example of a physical change. So these are types of physical changes. And then most of these terms, I assume that you know. So if we go from a solid to a liquid, what is that called? If we go from a liquid to a gas, and then we can actually go from from a solid all the way down to a gas. So this one, yeah, we're melting it. This one, boiling, evaporation, vaporization, any of those work. And then from a solid to a gas, yeah, sublimation. And then all of these involve, I just ran out of room here, these involve breaking bonds. Solid to a liquid, it depends what type of solid it is, right? It could be breaking covalent bonds, it could be breaking ionic bonds, it could be intermolecular forces. Liquids to gas, intermolecular forces. So these involve breaking bonds / intermolecular forces. These take energy. If you're going to break it, it's going to take energy to do that. And then the opposite, if I'm going from a gas to a liquid, if we're going from a liquid to a solid, and then we can go from a gas all the way to a solid. So a gas to a liquid is condensation. A liquid to a solid is freezing. And then gas to a liquid is deposition. And then these all involve forming connections, so forming bonds or intermolecular forces depending on what type of substance we're talking about. When we form these, we actually release energy. So be familiar with the names for the different phase changes. Know that phase changes are a type of physical change. And then know which ones involve making connections, which ones involve breaking connections. It takes energy to break them. We release energy when we make them. The other thing that I want us to know are the points. So something's boiling point. So not just the process of boiling, but the actual point at which it boils. What we're doing is we're going from a liquid to a gas, but that is actually at that point, it's actually in equilibrium. So the gas is going back to the liquid at the same rate. So liquid is forming gas, gas is forming liquid, and they're going back and forth at the same rate. So these would be equilibrium points. So my boiling point, right, we're at the temperature, at which I go from a liquid to gas is the same temperature that it condenses, that I go from a gas to a liquid. And the same thing with my melting point, right? The actual point at which it melts, we're going from a solid to a liquid, but then that liquid is going back to a solid, right? The temperature at which a substance melts is the same temperature at which it freezes, right? Water is going to melt at 0 degrees Celsius. It's also going to freeze at 0 degrees Celsius. So melting point and boiling point are actually the same point. So again, which ones are taking energy, which ones are releasing energy? We could actually relate this to our chapter 9 material, right? If it's actually absorbing energy, if it takes energy to do that, we're putting energy into the system, these guys would be considered endothermic, right? They're going to have a positive enthalpy change. These ones that are releasing energy, right? Energy is being given off. These are going to be exothermic. They're going to have a negative enthalpy change, right? If they're releasing energy, they have less energy when they're after they formed than when they started, so H final is less than H initial. And then again, remember, these are points where it's actually kind of stable. We could look at a quick, if I have temperature increasing on my y-axis and then just heat absorbed on this axis, as we go up, it kind of levels off. Those are my boiling points and my melting points. So kind of the heat and pressure is stable at those points where it's actually changing phases. So this point here, if I want to look at water, sorry, my lines are crooked. Let's actually just leave those off because those are too messy for me. We'll just label them. So melting point, and then boiling point. And then, of course, if we were going the other way, right, if we were starting up where I have a high temperature up here where it's a gas, right? And then I was going down here where it's a liquid, that point, right, going from the top down versus the bottom up, that would be my condensation point. And then down here I'm a solid, right? So that could be my freezing point. At those points again, right, we are in equilibrium, so it levels off a little bit for us.